On the coast of Cape Breton, near Glace Bay, Nova Scotia, the first thing left is absence. No towers, no pipework, no factory skyline where Canada once tried to build part of its nuclear future. The industrial complex is gone. What survives is scattered through sourced photographs, maps, documents, and memories of steel weathering under Atlantic salt air. Archival images restore the missing shape. Towers rise over the site. Pipes and tanks crowd together. Service roads cut through a plant far larger than the town around it would suggest. This was not a nuclear power plant, not a reactor, not the site of a meltdown. Glace Bay held a heavy water processing plant, a chemical factory built to make heavy water for Canada's CANDU reactors. Heavy water looks ordinary, but it contains deuterium, a heavier form of hydrogen. In CANDU reactor systems, that material mattered, and Glace Bay was supposed to help supply it. That distinction changes the story. The failure here came from industrial chemistry, public money, and steel placed in conditions it could not endure. The original plant alone ran to more than $100 million in period costs. Any billion-dollar framing has to be treated as a later dollar or broader rescue cost frame, not as the narrow original figure by itself. On one local shore, the promise gathered into a single image: Atlantic water, steel towers, coal town jobs, public money, and later, rust. Before the corrosion, before the takeover, before the ledgers turned ugly, the question begins with the place itself. Why was a nuclear supply megaproject built in Glace Bay at all? Glace Bay was already working ground. Coal had shaped the town long before the heavy water plant arrived, and by the 1960s, that foundation was under pressure. For generations, coal had shaped the rail lines, harbor traffic, town streets, and the rhythm of family life. Mines that had once made the region essential were becoming a problem governments could not ignore. The heavy water plant arrived with two promises attached. For Ottawa, it belonged to the nuclear age, a supply project for a country betting on CANDU reactors. For Nova Scotia, and especially Cape Breton, it looked more immediate. Construction payrolls, skilled jobs, replacement industry, and a reason to believe the next economy might be built where the last one was fading. The politics moved faster than the machinery. Premier Robert Stanfield and provincial leaders backed it as economic development for a region that needed work. In that setting, a heavy water plant became more than a technical proposal. It became a rescue plan made out of steel. That matters for where blame belongs. The workers and families who needed the jobs did not design the process, choose the materials, or set the terms of the gamble. They were asked to trust that a national industrial project could give a coal town a new engine. For a time, the idea had force. Take a region with industrial skills, ocean access, and political urgency, then attach it to Canada's nuclear future. The rescue plan still had to become a working machine. At Glace Bay, that machine would bring the ocean directly into the heart of the factory. The machine proposed for Glace Bay was a chemical plant, enormous, specialized, and built around a process associated with Jerome Spivak and deuterium of Canada. The process was called Girdler sulfide. In plain terms, it used ordinary water and hydrogen sulfide gas to concentrate deuterium, the heavier form of hydrogen needed to make heavy water. The plant did not create deuterium from nothing. It sorted out a tiny fraction already present in water, then repeated that separation again and again until the concentration became useful. On a diagram, it can look clean. Water moves through the system. Hydrogen sulfide gas moves through tall exchange towers. Temperature differences help shift deuterium between streams. Each pass changes the concentration only a little, so the plant needs height, circulation, pressure, and time. That rarity is where the scale comes from. Heavy water is valuable because deuterium is uncommon. To recover a small amount of finished material, the factory had to move huge volumes through pipes, valves, towers, and pumps. It also had to handle hydrogen sulfide, a dangerous toxic gas. The immediate hazards inside this plant were chemical and mechanical. flow, pressure, gas, water, and the materials holding them in place. The shoreline then entered the design. The plant needed water continuously, and the Atlantic was beside it. Cold, immense, and local, seawater looked like an abundant input for a project already under pressure to control costs. On paper, the shortcut had logic. Instead of treating water as something to import or produce elsewhere, the design could draw from the ocean at the edge of the site. In a plant like this, water is not background. Once it enters the pipes, it becomes part of the working environment. The next test was not only whether the Girdler sulfide process could separate deuterium, it was whether the factory's own body, its towers, pipes, valves, and metals could survive the water it was being asked to carry. Inside the plant, the blueprint met metal. The Atlantic water carried chlorides, salts that can be hard on steel in harsh industrial service. At Glace Bay, that seawater entered a heavy water process that also used hydrogen sulfide, a toxic gas with its own corrosion problems. Together, they created an aggressive environment inside the circulation system. Much of that system depended on carbon steel. That was the weak point. The pipe, valves, and metal surfaces meant to keep the process moving were exposed to conditions they could not reliably survive. Corrosion was not a surface stain on an abandoned building. It was inside the working body of the factory, where water and gas moved. Pressure had to be controlled, and flow had to stay continuous. In a plant like this, a damaged pipe is not an isolated problem. If a wall pits or thins, if a valve leaks or has to be taken out of service, the sequence breaks. If circulation cannot be trusted, the towers cannot do the slow separating work they were built to do. The intake decision did not stay at the shoreline. The cost-saving choice became a failure point throughout the plant. The ocean had looked like a convenient answer to an expensive supply problem. Inside carbon steel systems and a hydrogen sulfide process, it helped turn the factory against itself. This was chemical and mechanical failure, not a reactor accident. The damage came from chloride-rich seawater, hydrogen sulfide, and vulnerable steel brought together at megaproject scale. That is why the rust matters. It is the physical record of the mistake, not just an image of abandonment. The original plant did not merely suffer vague delays or ordinary startup trouble. Its process conditions attacked the systems it needed in order to work. Once the body of the factory was failing, the question changed. Could more money save the project, or would the rescue become another mega project of its own? Once the plant's steel body was failing, Glace Bay's heavy water project entered a different crisis. A factory built to supply Canada's nuclear program had become a financial loss before it had delivered usable heavy water. First, the original failure. Historical accounts describe the original Deuterium of Canada plant as failing before producing usable heavy water at all. That is the narrow claim. It does not describe the later ISEKL chapter. It describes the first version of the machine, the one that had consumed enormous money, including more than $100 million in period costs, and still had not fulfilled the purpose used to justify it. That number is the safer anchor, period dollars for the original failure. The larger billion-dollar label only works if it is clearly treated as modern dollar conversion, or as a wider accounting that includes takeover and rebuild costs. Without that distinction, the money story becomes too simple. Stopping there would have meant admitting that a national industrial rescue had collapsed in public view. Continuing meant handing the problem to a larger institution. Atomic Energy of Canada Limited stepped in. At this point, the paper trail changes. Takeover records, overhaul plans, repair programs. AAKL did not inherit a healthy plant waiting for minor tuning. It took over a facility whose first design had been damaged at the level of its working systems, and the response required extensive overhaul and rebuilding. This is why the simple line that the Glace Bay plant produced nothing needs care. For the original Deuterium of Canada project, it captures the failure, no usable heavy water before the takeover. After the rebuild, the later AAKL chapter was different. The site did operate for a period, even as the economics remained troubled. The rescue could make machinery run. It could not make the first decision cheap. Public money had moved from building a promised industrial future to repairing the consequences of the first attempt. The institutional chapter ends with closure and decommissioning, but the emotional end belongs back in Glace Bay, what remained for the place that had been asked to believe in it. What remains in Glace Bay is not the story of a town that failed. The people who needed this plant did not choose the materials, design the process, or decide that seawater should move through carbon steel systems in a hydrogen sulfide plant. They were asked to believe that a national nuclear supply project could also become a local economic lifeline. The structure that carried that promise was eventually decommissioned and taken down. The towers, pipes, and steel body that once made the site look permanent gave way to a quieter industrial absence. The chain is visible now, a cold region under pressure, a politically powerful promise of replacement work, a cost-saving seawater shortcut, corrosion inside the plant's working systems, more than $100 million in period costs for the original failure, a federal rescue and rebuild that can only be folded into a billion-dollar frame if the accounting is clearly stated, and finally, closure. That is why the Glace Bay heavy water plant matters beyond its ledgers and ruins. It was not destroyed by a reactor accident, and not by the people who worked in its shadow. It failed because a megaproject built around urgency and savings still had to obey the chemistry inside its own pipes. Public money could buy steel, towers, repairs, and time. It could not make vulnerable materials survive the environment it had been placed in. And in the end, the Atlantic that once looked like an answer kept moving past the shore, while the promised future built beside it disappeared into rust, paperwork, and memory. This was one rusted empire. There are others.